Welcome, folks. Today we are discussing a systematic review on heterogeneous material models for finite element analysis of the human mandible bone. It's a deep dive into the complexities of accurately modeling bone properties for improved simulations.
I see. So the main point is that there's currently no single best way to model the mandible bone's material properties in finite element analysis, right? There's a lack of consensus?
Exactly. The review highlights a significant lack of consensus on the optimal material model for estimating Young's modulus, a measure of stiffness, from mineral density in the mandible. They found 12 distinct heterogeneous material models, each with its own strengths and weaknesses.
12? That's quite a few. What are some of the key differences between these models?
Well, the differences stem from several sources. First, the origin of the models varies. Some are based on in vitro experiments, others on mathematical calculations, and some combine both. The type of experiment also matters. Tension tests versus compression tests, for example. And then there are differences in the bone samples themselves, the anatomical site, the size and shape of the samples, whether it's cortical or trabecular bone, and even the number of donors.
Interesting. So the quality of the data used to create these models?
Absolutely. The review assessed the risk of bias in the original studies that proposed these models. They used tools like Quinn and RobFeed to evaluate the quality of both in vitro studies and finite element simulations. Most studies showed low to moderate risk of bias, but there were exceptions. For instance, the Mimic's empirical default formula, a widely used model, lacks transparency regarding its development and reliability.
That's a significant concern. What are the implications of using these models?
The variability in the models leads to significant differences in the estimated Young's modulus. This directly impacts the accuracy of finite element analyses. Using an inaccurate model can lead to unreliable predictions of stress and strain distributions in the mandible, which has implications for implant design, fracture fixation, and other clinical applications.
So, what recommendations do the authors offer to address this issue?
They suggest several things. First, researchers need to be more careful about selecting appropriate models based on the specific bone domain, density range, and directional behavior. They also emphasize the importance of clearly reporting the material assignment method used in the analysis to improve reproducibility. And crucially, they call for standardized experimental protocols and validation methods that combine simulation and experimental approaches.
And what about the future of this research? What are the next steps?
Future research should focus on developing new, more accurate models specifically for the mandible bone, taking into account its anisotropic nature, meaning its properties vary depending on the direction of force. They also need to investigate the influence of factors like sex, age, and ethnicity on bone properties. A comparative finite element analysis is also needed to assess the impact of different material models and assignment methods on the results.
It sounds like there's a lot of work to be done to improve the accuracy of mandible bone modeling in finite element analysis. This review provides a valuable overview of the current state of the field and highlights the need for standardization and further research.
Precisely. This systematic review provides a crucial foundation for future advancements in this area. By addressing the challenges highlighted in this study, researchers can significantly improve the accuracy of subject-specific finite element analysis, leading to better clinical decision-making and treatment outcomes in the craniomaxillofacial field. Thank you for listening, folks. Goodbye.